My name is Colin Whitaker. I'm an engineer on our anti-phishing team. It's my pleasure to introduce our speaker today, Justin Ma. Justin is a PhD candidate at UC San Diego. He is advised by Stefan Savage, Jeff Volker, and Lawrence Saul. His interests include systems and networking with an emphasis on network security and machine learning. So with that.
Thanks for the introduction, Colin. And thanks for inviting me up to Google to give this talk. So today I'm going to talk about something that hits pretty close to home for a lot of people. In particular, this may be something that you or someone you know happens upon, not necessarily on purpose. So there are a bunch of bad websites out there. Some may be selling spam advertised goods, such as counterfeit drugs, watches, and so on. Trying to sell you counterfeit or illegal things, through spam and other nefarious channels. Or you might happen upon sites that encourage you to download postcards or funny like screensavers and whatnot, which in fact are malware masquerading as legitimate programs. And furthermore, you might happen upon phishing sites which attempt to imitate sites that you are familiar with, but with a purpose of stealing your credentials. So in this example down here, I'm showing a picture of the Facebook login page and also a phishing attempt to imitate that Facebook login page. So there are a lot of bad things out there, and the way we happen upon them are by visiting their URLs. So in the course of our normal email browsing or web surfing, we'll encounter links, and the typical user may have a difficult time distinguishing between a safe URL and a malicious one. In particular, when you take a look at these few examples, 2 of them are malicious and 2 of them are not benign. So one of them might be pretty easy for a lay user to pick out. Right? For example, the example on the top has a lot of random jumble of characters and numbers and such. But then the next 2 might be a little bit of a harder distinction to draw from there. And if you find the last one suspicious, I don't blame you. But the bottom line is that we'd like to predict what is safe to visit without committing to risky actions. So to that end, the problem in a nutshell is that we want to use the features related to URLs to identify malicious websites. So we're going to do this without context, and that is regardless of the context in which the URL appears. So it could appear in emails, web searches, embedded within pages, and so on. And we'd like to do this without using the content of the page. Now, there are different classes of malicious sites. We're just going to group them all together and treat this as a binary classification problem, that is distinguishing benign from malicious sites. So when we're faced with a bad site, we would like to give them our universal stamp of disapproval. And the canonical application I'd like you to have in mind is that of a reputation service, just as an example. So, a person visits a URL, submits a URL to the service, which in turn gives you a rating, a prediction that, yes, I think this is going to be safe to visit or unsafe to visit. Now, how would you do this at first glance? Well, at a first cut, you might be constructing a blacklist. Say we compiled a list of known malicious domain names and kind of kept a little database of them. Or we might pick little aspects of the URL, things that we've attributes that we know just due to our domain expertise that might work, and train a simple machine learning based classifier on them. And as it turns out, this is the state of the practice. There's various blacklisting services out there, and there has been work on kind of learning on hand-tuned features. But this comes with some limitations. Especially with blacklists, you can't learn from the newest examples. And with learning on hand-tuned features, you can't take advantage of the newest features for classification. And in this arms race, between spammers, phishers, and other people who construct malicious websites, a fast feedback cycle is critical. Being able for the defenders to be able to catch up quickly is important. And so to that end, we ask, is there a more automated approach to solving this problem? Now with that, the contributions of this work, we build a URL classification system that is used by large webmail providers. And in particular, we kind of demonstrate that large-scale machine learning can be practical for this computer security problem, where our particular emphasis are using large feature sets and online learning. And I want to acknowledge the work by the anti-phishing team, who have approached the problem in a similar vein, and for making the web safer for a lot of us. So I've just given you an overview of the problem, and today I'll talk about the first segment, Moving Beyond Blacklist, which presents a preliminary study of the features that we use. And then I'll talk about large-scale online learning, where we want to scale up our approach to millions of examples and features. So in this first segment, we ask, well, do we have a feature set for classification that works? Now for now, we're going to focus on batch algorithms, just because this is more of a feasibility study than anything else. And we'll work with data sets that have on the order of 10 to the 4 examples and features. I'll provide an overview of the system that we use for classification. And then I'll talk about the features, like the various different features that we considered before settling on a particular feature set, as well as experimental results. So this is an overview of our system. It has 3 components. The first, we have to have training data, labeled examples of known malicious, known bad URLs. But then these are just URLs themselves. They don't provide us any more information beyond that little text string. So we actually construct a system that collects geographic, WHOIS, DNS, and other sorts of information based on that in order to convert that into a canonical mathematical form, which we use for classification, vector notation. And so for those who want, who are interested in seeing kind of concrete machine learning notation related to these, we've got labeled examples. We construct a feature vector X related to them, and then we want to construct a hypothesis function that gives us a rating that I think this is likely to be good, I think this is likely to be bad. So I'll quickly go over our sources of labeled data and what we use for classification for this segment of the talk. So in this segment, we had these data sets. We have 2 malicious sources and 2 benign sources, which we mix and match to construct 4 different data sets. So the malicious sources, one's a phishing source, the other is kind of a generic spam sink, which contains phishing links. And the benign URLs we draw from the Yahoo web directory as well as the DMOZ open web directory. And when we combine these sets together, they have on the order of 30,000 to 55,000 features. As for the algorithms, I'm going to show you results that we had for logistic regression with L1 regularization. We had similar accuracies when we used support vector machines, both with linear and nonlinear kernels, all of which performed better than naive phase. So with that, I'll talk about the different features that we considered for the R system. Now, to give you an overview of feature vector construction, we're given a URL, and we'll identify maybe some lexical features related to it, and then we'll look up information based on the host itself. Now, what happens from here is that we convert these sort of values into real valued features as well as a host of binary host space and lexical features. But when we're considering features, we could start with something very simple, or we could move on to something that's a little more comprehensive, a little more complex. And so I'm going to present kind of the 5 fundamental feature sets that we considered in increasing order of complexity. So the first are blacklist queries. So we construct a bit vector where for each service that we're querying, we get a yes/no answer, whether it's in a blacklist or not. So I want to emphasize, though, that this is not comprehensive. As I'll show later on, we actually use these as a subset of our whole feature set, but they don't provide the entire answer. The next set of features we consider were those that were kind of manually selected for previous studies that use machine learning. So in particular, they include whether there's an IP address in the host name, how many dots are there in the URL, right? Because very long host names look kind of suspicious to us. And we also look at the WHOIS registration date, because things that were registered more recently, you have reason to believe, are a little more suspect. Now, to that end, we wanted to consider WHOIS features by themselves as kind of a fundamental feature set, but not only their dates of registration, update, and expiration, but also the registrant, that is, who the site was registered to, and also their registrar, that is, who manages the domain name registration. So in this example, you might have a set of domain names that were registered yesterday by one particular company, by a rather suspicious company, and we want to be able to use that as a feature for classification. And then we consider host-based features, which take blacklists and WHOIS as a subset. They incorporate those, but introduce other information as well, in particular features related to the location of the host on the internet. And I'll give you a particular example. So Mikolo was an ISP that used to exist back in late 2008. And they were responsible, they hosted the command and control infrastructure for bots that were responsible for sending 40% of worldwide spam at the time. So after their takedown, like the volume of spam dropped dramatically, as shown by this graph that was generated by SpamCop. Right around November, the spam volume plummeted dramatically, and that tells us that there are bad ISPs out there. And so to that end, the features that we use include IP address related features, which autonomous systems, which IP prefixes do these sites appear in, features related to the domain name system, the DNS features, as well as geographic features, where is it located exactly, and so on. To that end, we'd like to be able to use this location information as a feature to help us distinguish good from bad sites. And finally, the last fundamental set of features that we consider are lexical features. That is, features that help us describe the fact that malicious URLs will look different from benign URLs. So to that end, we look at tokens in the host name as well as the path. We distinguish between host name and path, as well as length of the URL and the number of the dots. And so to that end, we wanted to ask, well, how do they do? So what you're seeing here is a graph. The histogram on the y-axis shows the different feature sets that we considered, and the x-axis is the error rate. That is the total number of mistakes made over the data set. And the 4 different colored bars represent the 4 different data sets that I mentioned earlier. That is the result of mixing and matching each of the 2 benign sets with each of the 2 malicious sets. Now off to the right, you'll see the number of features that are present in the Yahoo fish tank combination, represented by the cyan bars, but the number of features in the other combinations data sets were similar. Now what you're noticing here, though, is that the more features that we use, the better classification that we're getting. All right, yeah, go ahead.
Is that the sum of false positives and false negatives?
That's correct. Oh, yeah. The question was, is that the sum of the false positives and false negatives? And that's correct. Yeah, that's what the error rate represents. But host-based and yeah.
So in the WHOIS case, the number of users, is that essentially the number of distinct registrants and so on?
Yeah.
These are mapped to binary value variables.
Right, registrants and registrars. We looked at it's sort of a bag of words over the tokens and the names of the registrars and registrants. Yeah.
It's just unintuitive to be so. I was just curious about it's sort of unintuitive that there'd be so many more lexical features than WHOIS features, since I would imagine the universe of WHOIS registrants and addresses and so forth to be very large.
Yeah, and actually, I'll show you some data later on in the second segment of the talk, where you'll see kind of how the number of features grows over time and the relative number of host-based versus lexical features. So host-based and lexical features are kind of complementary. So what happens if we combine them, right? then what we get are the full feature set for the Yahoo fish tank set on the order of 30,000 features. And we get the best classification rates, at least for this, for this study, which gives us about 96 to 99% accuracy. Now you may be wondering though, well, you incorporated Blacklist as features. I feel like you're getting too much leverage from that. Or you might say to yourself, well, WHOIS features, they're so hard to, such a high overhead query operation, right? Because WHOIS is not structured like DNS is structured. So, what have we omitted Blacklists? What have we omitted WHOIS? Will we get worse results? And we do, but not by much. And so this tells us that although they're useful, Blacklists and WHOIS information are not comprehensive. And to sort of further drive the point home, I'm going to show you a couple of ROC curves comparing Blacklists to full features. The full features being the combination of host-based and lexical features. Now, for those of you who aren't familiar, an ROC curve is sort of a sensitivity plot telling you how well will a classifier perform if we set different thresholds for the decision, sort of different decision thresholds. So, classifiers produce a rating, a number. If it's higher, it tells us that it's more likely to be malicious. If it's lower, it tells us to be less likely to be malicious. But we have to make a binary decision saying like, yes, we're going to throw it in the malicious bin. Yes, we're going to throw it in the benign bin. And to that end, the decision threshold is an important value to set. If you set it lower, you're probably going to get more likely to classify things as malicious. And if you set it higher, you're more likely to classify things as benign. And so what this curve shows is what happens if we try different values of the decision threshold. What if we trace out a curve and see what the results are for classification? So what you're seeing here are the ROC curves for the Yahoo fish tank data set. The x-axis shows the false positive rate, and your eyes are not deceiving you. It's going from 0 to 1%, whereas the y-axis is the true positive rate, which is going from 0 to 100%. So I scaled things a bit on the x-axis. And what you see here is that for a given false positive rate, say 0.1% false positives, we're getting much better true positive rate when we're using full features as opposed to the blacklists. So we're able to detect malicious URLs, at least in this particular segment, with only using the URL features. And a diverse feature set helps, giving us 99% accuracy with 30,000 plus features. And I go into more detail about the models and how things turned out in the KDD 2009 paper. But this is only with data sets that have on the order of 10 to the 4 examples and features. What happens if we scale this up? What happens if we make this more adaptive? And that's the focus of this next segment. So as far as the system itself, a lot of it is similar, except this time the training feed is live. We have new examples that come in on a daily basis. To that end, our infrastructure has to be able to query features, host-based features, and so on, in real time, quick enough so that we can get our features, our vectors, in time for classification. So the main question we want to answer is like, well, given that the features that we showed in the previous segment are promising, how do we scale it to live, large-scale data? So I'll give you an overview of the live training feed, and then I'll talk about the challenges that we face in terms of scale and non-stationarity of the data. Non-stationarity being that the features that characterize malicious and benign URLs, they'll change over time. In the evaluations, I'll talk about the need for large and fresh training sets, and as well as making the case for online learning. So the live training feed consists of a feed of malicious URLs, about 6,000 to 7,500 coming in daily from a webmail provider. And then we supplement that by picking out benign URLs from the Yahoo Web Directory. This gives us a total of 20,000 URLs per day. Now in this experiment, we collected data over the course of 4 or 5 months, 120 days of data. So this gives us more than 2 million examples. Now, we construct features the same as before, but this time, we've got on the order of millions of features, and even by day 100, things will continue to grow beyond that. In particular, a lot of these new features are the result of kind of new binary features that are being introduced. They're the result of enumerating tokens, lexical tokens in the URL, as well as enumerating ISPs, like their autonomous system numbers, as well as their IP prefixes, enumerating registrants, and so on. 2.9 million features after 100 days. And in this graph that you're seeing on the lower left, it's the x-axis is the number of days, and the y-axis shows the accumulated number of features that we encounter over time. It's not as if that these features are useless. One example I'll bring up, early on, just before day 10, there is a company called Dual Management Media that's responsible for registering 27 different sites. And so being able to use the fact that the registrant is Dual Management Media will be a useful feature for classification. And I think you had a question earlier about the relative number of host-based and lexical features. And so, yeah, lexical features do outnumber the host-based features, but you get a relative idea of the ratio right there, about 1.8 to 1.1. So, millions of examples, millions of features. We think that online learning might be a promising avenue for addressing the problem of training a classifier in this kind of larger scale environment. And that brings me to kind of the practical challenges that people face in these industrial scale applications. Scale is important. Millions, perhaps billions of examples are encountered. And then non-stationarity is a key thing that we have to address as well, because examples will change over time, because there's this constant arms race with criminals. Things are evolving. So pivotal decision that we have to make is whether we want to go with batch algorithms for learning or online algorithms. So to give you an overview of batch and online learning, well, batch algorithms typically consist of a lot of things that we're familiar with, support vector machines, logistic regression, and so on. But the key thing is that they make multiple passes over the data to train the classifier. And so incremental updates are not, they're pretty difficult to do in that framework. And so there's potentially, and because you're making multiple passes over the data, there's potentially high memory and processing overhead. Contrast that with online learning, which consists of the family of Perceptron style algorithms that make a single pass over the data, seeing each example only once, and can make incremental updates, that is, updating classifier one example at a time, and as a result would incur lower memory and processing overhead. To that end, we believe that online learning will help us address the problems of scale and non-stationarity in this scenario. So with that, I'll take you through the evaluations that we did over the 120-day dataset, making the argument, for the need for large and fresh training data. We'll compare different online algorithms, and then we'll make the case for continuous retraining as well as growing the feature vector, that is, adding new features over time. So you'll be seeing a series of graphs that look like this. Basically, on the x-axis shows the number of days over which the experiment was conducted. The y-axis shows the cumulative error rate, that is, the number of errors made so far in time. So this includes both false positives and false negatives. And here you see two curves. The black curve represents the support vector machine with a linear kernel, which we're going to treat as our canonical batch algorithm, trained on 1 day of data, day 0, and then fixed and used for classification for the rest of the 120 days. And as you can see, the error rates get steadily worse over time because it's only trained on 1 day of data very early in time. Compare that with the purple curve representing the SVM that's retrained daily. So, for example, on day 60, the SVM retrained daily is trained on day 59's data, only 1 day of data, and then tests on day 60's data. And so this process is repeated on a daily basis, and you can see that the error is better. What this tells us is that fresh data helps with classification. but we're only training on 1 day's worth of data. What happens if we expanded our training set? Well, then you get the following. So the blue curve is the kind of multi-day analog to the black curve. Here, we're training on 2 weeks worth of data, which is as much as we could fit in the memory of the evaluation machine. And then after 2 weeks, we fix the classifier and use it for testing over time. The green curve is the sort of large data analog of the purple curve. Here, we're training on a sliding window of 2 weeks of data. And we use that for, that's the process that we use for training and classification in that case. The fact that you can see the blue and green curves are improved over the previous curves tells us that having more training data helps. Now, I'll take an aside. So since this segment is about online learning, well, we have to ask, well, which online algorithm helps in this case? And I'll present you 3 examples of online learning algorithms that sort of represent points in the design space ranging from simple to more complex online updates. And I'll explain them briefly. So first we take a look at the Perceptron. This is a popular algorithm because it has a finite bound on the number of mistakes that you can make if the data is separable. So if you can imagine that the URLs, the feature vectors, are points in a very high dimensional space, then we're trying to train sort of a plane we're trying to train a plane that cuts between the malicious and the benign examples. And the update's very simple. You just change the direction of the weight vector to point in the direction away from positive examples towards negative examples. And yeah, it's just as simple as that. The problem is, though, it's very coarse. Which brings us to logistic regression with stochastic gradient descent. So I don't know if you're familiar with logistic regression or not, but the idea behind logistic regression is to train that decision boundary, that hyperplane, so that you can maximize the likelihood that it separates the data. And when you're doing stochastic gradient descent, though, you're training this decision boundary one example at a time. And that brings me to the update that's in the middle right there. Now, one thing I'll point out, it looks a lot like the Perceptron update, except now it has this little constant in front, which is adjusted based on what I'd like to call a proportional update. So what happens in online learning is you try to classify an example coming in, and then you're told, well, it's actually malicious or it's actually benign. And with a proportional update, based on how severely you misclassify the example, the update will be tuned, the magnitude of the update will be tuned accordingly. So for example, let's say that y of t is +1, that is, it's a malicious example. And then our prediction function, which is sigma of the inner product of the weight vector in the example, let's say that that's, let's say it's 0. Like we think it's benign, but it actually turned out to be malicious. Then delta will be its maximum possible value of 1. It'll be a full update right there. Whereas if we predicted that it was more likely to be, say, 80% likely to be benign, even though we classified correctly, we're still going to update our model anyway, but only by a little bit. That's what a proportional update entails. And then finally, the last step in this progression is confidence-weighted learning, which is a recent development, came out in about 2008. And the idea here is instead of having a single weight vector that characterizes our classifier, our weight vector will actually come from a distribution, a Gaussian distribution which has a mean and a covariance, where the covariance represents our uncertainty about the estimates of the individual feature weights. So it's formulated as a constrained optimization problem. I'll go over this briefly with you, where you want to find, so argmin of mu and sigma, that is, you want to find new model parameters, you want to find a new classification vector mu, and a new uncertainty matrix sigma, so that the KL divergence between the new model and the old model, so you want to minimize the KL divergence between the new model and the old model, so that the probability of YWX is greater than 0, that probability is greater than eta. So what this means is that, so YWX is the classification margin. This is a term in machine learning that tells us that, well, that tells us how correct our classification is. And if it's greater than 0, it's correct. If it's been less than 0, it's incorrect. And the math works out so that, you know, if it's a false positive or if it's a false negative, correct classification still means that the margin is greater than 0. And so we want to be able to classify this newest example, x of t, correctly with greater than probability eta, some confidence value. So we set eta to 90%. So what this is saying is that we want to change our model as little as possible so that we can classify this latest example, which we might have misclassified, so that we can correctly classify it with greater than some confidence. And as it turns out, you can express this as a closed form update of mu, of the weight vector, and the covariance. And I just wanted to point out that the mu update looks a lot like the perceptron, but this time you've got a matrix in front of the example x. And what this does is it updates features at different rates. Now, because storing a full matrix, you know, million by million or even larger is not, you can't store that in memory, we actually represent it as a diagonal covariance matrix so that there's an uncertainty value characterizing each feature weight alone. And so what this will tell us is that if a feature weight has high covariance, if it has high variance, that means our estimate of that is more uncertain. And so we're going to update that because of the sigma x multiplication down here. We're going to update that feature more quickly than if we had a feature weight that had low variance, that we had higher certainty of. That feature will be updated at a slower rate. So that's what the confidence weighted learning algorithm does. Any questions so far on this? Okay. So I'll show you here the results for the different online learning algorithms. So here are the results for the Perceptron. It does okay, about 2% cumulative error over the course of the experiment. But then here are the results of logistic regression with SGD. What we see is that the proportional update helps improve the classification results. But if we compare that to confidence-weighted learning, we see that using per feature confidence really helps. And I think it's worth mentioning, I think according to the NDSS 2010 paper, my understanding is that the Google machine learning algorithm that you used is sort of a version of, it's like a batch version of logistic regression with stochastic gradient descent, but probably with a bunch of other things added in as well. And so you can kind of think of LRSGD as like that, but making only a single pass of the data as opposed to making multiple passes over the data, because you could benefit with multiple passes over a single, as opposed to a single pass. So let's take it back to the batch algorithms that we evaluated before. We saw that fresh data helps. We saw that more data helps. But when we compare that to confidence-weighted learning, we see that online learning matches batch learning. Actually, in this case, it does better. But you know, to be on the safe side, we can say for sure that with online learning, you can do at least as well as batch. But why is that? So I'll compare confidence-weighted learning with the best batch learning curve, where we had a sliding 2-week window of training data. So the key difference here, though, is that with the SVM, we're only retraining once a day. Whereas with confidence-weighted learning, we're retraining after every single example that we encounter. So that classifier is being updated, you know, 20,000 times a day. So what happens if we sort of, you know, level the playing field? What if we had a version of CW which retrained only once a day? Well, then this is what you'll get. This is the result. The purple curve here you're seeing is the result of confidence-weighted learning, where we only update the model after the end of each day. So you see that it does worse initially, but then eventually it overtakes batch learning. And this is kind of the fundamental trade-off that you have to make when you're using online versus batch learning. Because I mean, given the same amount of data, a batch learning algorithm is going to do better because it can make multiple passes over the data. But if you're in a regime where you've got lots and lots of data, where it's infeasible to store it in memory for a batch algorithm, then you might want to consider online learning for your purposes, even if you're only updating once a day. But the difference between the red and the purple curve tells us that continuous retraining really helps here. Finally, we ask, well, all right, so you're adding new features over time. Is it worth the effort, right? And what you're seeing here with the purple curve is this time it's the online learning algorithm, CW, but with a fixed feature vector. That is, we only consider the features that we saw up to day 1 in the experiment. And then we train over the course of 120 days, and this is the result that you get. And when you compare it to the original CW result that we showed, it's doing worse. And so growing the feature vector helps with classification, considering new features. But this is for CW, which is the more complicated online learning algorithm. Do we get the same benefit when we say, grow features for the Perceptron versus not growing the features for the Perceptron? Well, this is the curve results for the Perceptron with the fixed number of features. And here's the curve for the Perceptron with a growing number of features. The improvement is marginal, right? But remember that the Perceptron and confidence-weighted learning are fundamentally different algorithms because confidence-weighted learning has that per feature update rate. And what this tells us is that growing the features and accounting for that per feature confidence really helps with classification. So given these results, we wanted to sort of build a proof of concept browser plugin just to see how this works. And what you're seeing here, let's say that you're browsing the web. So here I'm browsing Gmail, and my toolbar is telling me, well, I think this is a 93.8% safe page to be on. And I mouse over a link in my email that says, to continue, click here to log into your authorized.net account. Now, for those of you who aren't familiar, authorized.net is it's a company that helps merchants process back-end transactions for web commerce. So you can imagine that if you were to compromise someone's authorized.net account, that you could get access to whatever money they've accrued from online commerce. So I mouse over that link, and the plugin tells me, well, this site is about 0.6% safe to visit, probably not a good idea, but I want to get more details. And so I mouse over that prediction bar, and it tells me that, well, and here's the reason. Various different features had different weights, and these were the top 10 malicious and top 10 benign features that were part of the prediction right here. Okay, well, I decided to ignore that, and I click through anyway. So the browser lets me visit, and this is the site. It kind of looks like a cheap knockoff of this site. This is the real authorized.net. So I have my suspicions. I don't go any further. This was on a Thursday. I casually checked it later on. It turned out to be blocked later. And the idea here is that, well, the browser had a blacklist. It was tied to a blacklist. But if you had a predictive, if you were using a linear classifier instead, which helped predict whether it was positive or negative, you probably could have gotten that warning a little earlier on. Of course, there are implementation issues with respect to deploying a classifier as opposed to deploying a blacklist, but we can definitely talk about that later. So we wanted to tackle the problem of detecting malicious URLs. It's a relevant real-world problem, and it was a successful application of online learning. In particular, what helped were having lots of fresh training data, as well as having trained the model continuously and growing the number of features. And in particular, when we compare confidence-weighted online learning with the batch learning, it can be as accurate, but more adaptive, and use fewer resources. And with that, I'll wrap up. So as far as kind of public exposure, we've released a data set, actually, an anonymized 120-day subset of our data, so that it can hopefully act as like a benchmark set for people who are interested in developing online algorithms. And in terms of industrial impact, there are mail providers who have adopted our approach for classifying URLs in their email messages. And I have the link up there for our project page in case you're interested. And with that, I'll conclude with some final thoughts. So I work in systems and machine learning, kind of the intersection of the two. And I like working in systems because it's kind of a source of high impact, large scale applications, things that the everyday person can relate to. At the same time, machine learning kind of gives us methodical approaches to tackle these problems. But when you're tackling these problems, you have to kind of acknowledge the fact that there are these real world constraints that we have to, there's limited processing, there's limited memory, and we have to deal with that. And to that end, I believe that machine learning is more than just, a plug and play solution. You have to be aware of, the constraints that you're dealing with. And so to that end, when you consider the interplay of systems and machine learning, embracing the real world constraints, but also embracing the possibilities that machine learning have to offer, you can come up with kind of interesting solutions to important problems. And this work, I believe this work on detecting malicious URLs is one example of that. So with that, I'll take your questions.
So I saw that to simplify the implementation of your continuous weighted
Confidence weighted?
confidence weighted,
Yeah.
the confidence weighted algorithm, you only use the diagonal of the covariance matrix.
Mm-hmm.
How does this affect situations where two features interact very directly, like in an XOR relationship?
Yeah, I think you do lose a little bit. The main reason that you want to use the diagonal covariance is to save runtime overhead and memory. And you do lose something in terms of accuracy. Actually, I have an AI stats paper that I'll be presenting later this month, which talks about what happens if we try to approximate the full covariance structure during learning for the confidence weighted algorithm. And you actually get some improvement. Of course, you get more processing and runtime, more processing and memory overhead as well. But it's true that there are correlations to exploit in this application. It's just that we'd have to develop methods that do that scalably. Yeah.
Thank you. Are there any questions from the VCs?
So I noticed that your system, can you go back to the example with, your system seemed to have most of the weight coming from the word logon. It seemed to have learned that anything with the word logon in it is a bad, URL.
Sure. Wait, which one? Yeah, this example? Yeah.
Is that in fact most of the weight? I don't know. What are some other examples of features that your system thought were very interesting?
So other examples of interesting features were, WHOIS registration date is actually a very important feature. Just because it mimics, it reflects the reality that malicious folks are trying to re-register sites constantly because they get taken down. I think that the host-based features, in particular the AS numbers and the IP prefixes, were actually pretty important because they sort of that provided a level of granularity for separating good parts of the internet versus bad parts of the internet that was useful for classification. So yeah, WHOIS, host-based stuff. I think that was pretty important. Yeah. Yeah, I noticed you're pointing out the fact that logon gets a very high weight here, but as we saw in the previous segment where we're comparing different feature sets, I think even if you were to consider that, there would be enough other features that would be weighted negatively for this. Yeah.